Okay, so so the main topics in chapter 5 is about continuous random variables. Okay. All right, but in the first two sections, okay, in the first two sections, I will also cover properties of general random variable, not only for continuous random variables. Okay. Okay, so we first of all recall the definition of the cumulative distribution function CDF, okay, of a random variable x. Okay. So f of x, the CDF, is defined to be the probability that of the event that x, random variable x, is less than or equal to d to x. Okay. Okay. And we have listed 6 basic properties of the CDF of a random variable x in proposition 4.10.8. Okay. So in the last section of chapter 4, okay, so there we did these 6 properties. Yeah. All right, and here I would like to state one more properties of a CDF in proposition 5.1.a. So we let f of x be the CDF of a random variable x. Okay, then f of x has a finite jump at each point of discontinuity. And has countably many points of discontinuity. Okay, so let me draw a figure of a CDF. Okay, and as we know from proposition 4.10 point A that the CDF has value in between 0 and 1. Okay? So this is 0 and this is 1. So f of x. So this is from the first property. Then the second property in proposition 4.10.8 is that the CDF is an increasing function. Okay, all right, and of course we cannot guarantee that the f of x is continuous function, right? In general, so suppose that here it is, say, is a discontinuity here. Okay, so before A1, okay, we have a discontinuity. Okay, and as we know, when x goes to minus infinity, the CDF goes to 0, and if the, say here, and if x goes to past infinity, the function value goes to 1. Okay, this is property 3 and 4. Okay, now, and property 5 says that it is right continuous. Okay, so suppose that we have this one. So at this point, so we have right continuity here. So that the right limit at x equal to a1 is equal to the function value at a1. Okay, so that we have a solid dot here from the right hand side, but from the left hand side, because this is a discontinuity, so that we have a circle here. Okay, but we still have the left limit. Okay. All right, so let me describe that. So this is the, I think the gain is too much. Okay, let's see that. So this is say this is AI here, etc. Right. So this value in here we have f of AI, which is equal to f of AI plus. And in here, we have f AI minus. So this is the left limit. Okay. Similarly, we have f of AI, 1. This is 1. Sorry. 1, 1, 1, yeah, equal to f ai plus. This is f of ai minus. Okay, right, and so we look at here. So we include for this interval, okay, we include the right end, but exclude the left end here, because that we have a circle, okay, in general. All right, so you can see corresponding to a discontinuity at x equal to a sub I, we have an interval. Okay? So this is an interval here. AI minus here. Okay? So we have an interval. And as you can see, for different discontinuities, the corresponding intervals are non-overlapping. Okay, so let's see the proof. We let A sub I in the index set capital I be the set of all points of discontinuity okay. One of the conclusions in proposition 1.1.8 is that the index set I should be countable. Okay, so we want to show that I is a countable set. Okay. Now, since f of x is a right continuous increasing function on R with a left limit at each point of discontinuity by properties two, I think property 2 is increasing, and 5 and 6 in proposition 4.10.8. Jumps correspond to non-overlapping intervals f sub a I minus to f sub a I at the points a sub I of discontinuity. Alright, and with we know f of a I minus is less than maybe I at points of discontinuity with f of a I minus less than f of a I, so that we have a jump. Okay. Any questions? Okay. So this is very important. Each jump corresponding an interval, and these intervals are non-overlapping. Okay, you can see that. So this is from the property that f of x is very continuous and increasing, and at every point of discontinuity, it has left limit. Okay, left limit. Okay. We know that this is probability that x less than a1. This is probability that x less than ai. Okay, so we know the left limit is just this probability. Right? Okay, so now the jump size at x equal to ai is just f of ai minus f of ai minus, and which is finite by property 1, because property 1 in proposition 4.10.8, because the function value is between 0 and 1. Okay, so they have so that the difference must be, so the jump size must be finite. Okay, so that so has a finite jump. Okay, at each point, and the reason why the index say I, capital I, is countable is here, since rational numbers are dense in the real line. This means that rational number is everywhere in the real line, okay? So it's dense. Each non-overlapping interval f of ai minus to f of ai. Okay, so each non-overlapping interval has a distinct rational number in it. Okay, so we select a rational number in each non-overlapping. So suppose we just take this one, because rational number is dense, right? So in each interval, which we know of course is non-empty, we can pick up one rational number. Okay. Actually, there are infinitely many rational numbers, but we just pick one. And here, pick one, right? So they are rational numbers, and that they must be distinct. Okay, because they are in non-overlapping intervals. Okay, so each non-overlapping interval has a distinct rational numbers. But the set, since the set of all rational numbers is countable, so we can count all rational numbers 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we can count them. So the set of all rational numbers is countable, right? That's the number of jumps, okay, is also countable. Okay. Okay, so the number of non-overlapping intervals is countable. Okay, and each non-overlapping interval corresponding to a point of discontinuity. So the number of points of discontinuity. Okay, so that's the index say I is countable. So this is the characteristic of a CF. So if the CDF of a random variable is not a continuous function, then it has only countably many points of discontinuity. Okay. Any questions? Yes?
Is this the same that we use for calculating probability mass function from CDF?
Yes, so that means that, yep.
That's right.
Yes, for CDF, for the probability mass function in general, there are only a count of many points which is positive. When we define probability mass function, right, for discrete quantum variable, of course, that the PMF is 0 except a count of many points. All right, and this point are possible values of discrete random variables. Okay, so for discrete random, of course, the PMF has these properties. Now, this proposition, maybe I make a remark, so you ask a very good question. So the probability mass function, P of x, of a random variable, not necessarily discrete, just a random variable, okay, is 0. Okay. For all x in R, except at countably many x by proposition 1.1.8. The reason is that we know this is okay, so that the PMF, probability mass function, we know this is probability of okay. So this is f of x minus f of x minus. Okay. Now, if if the probability mass function is positive, we have a point of discontinuity, right? So if this difference is positive, which means that the CDF F, capital F, has discontinuity at x. Okay. But we know there are only countably many points of discontinuity, so that this is positive. This is positive only for what? For countably many x. Okay. Or you can say at points of discontinuity of f of x. Okay. And which are countably many by proposition 5.1.8. Okay, so we can say that. So this property of PMF is general for any types of random variable, discrete, continuous, or not discrete, not continuous anyway, just arbitrary random variable. For any random variable, the PMF has the same property. Okay, so the PMF is 0 for all x in R except at countably many points. And specifically at points of discontinuity of the CDF. Okay. Other questions? We can use CDF of a random variable to compute the probability of events described by a random variable. Okay. So let X be the CDF of a random variable x. Then, for any A, B, in between minus infinity and past infinity, we have one, the probability that x is in this half open, half closed interval. Okay, so you can see this is an event which is described by random variable x, right? So this is an event of interest. Okay. And we know that sometimes we just write in this way. Okay. And this probability could be computed. This is just equal to f of b minus f of a. Okay. Second, the probability that x is in between this open interval, which is probability A, less than x less than B, and this is f of B minus f of A. Okay. Third, probability that x is in A, B, another half closed half open interval. So this is f of B minus f of A minus. Okay. The first one, probability closed interval. So this is P, A, this is, then this is equal to B minus f of A minus. Okay. And the fifth one, for a point, of course, this is P of A. So CDF contains all the informations to compute the probability of an event of interest described by a random variable x. Okay, so basically you can see. All right, so but these are spatial. These are all intervals, right? And then they are basic types of Borel set. Yeah, and so you can see here. And then the proof actually is quite simple. So we see that we know that we know this. Oh, maybe this is too narrow. Maybe right here. First of all, 1. Okay, so now we know X, this event is the disjoint union of this event okay? Right, so this is the event that consists of all outcome omega whose value under the random variable of x. We model a random variable x as a measurement device. So the measurement result, okay, x less than b. All right. So all the values, function value less than b, is equal to all the value less than or equal to a, or bigger than a but less than equal to b. Right? So this is the disjoint union. Okay. So this event is the disjoint union of these two events. Right? And so by the countable additivity, right, of plus probability that, okay, this is from the countable additivity of probability function. So this is implies that, so this one, okay, it is the probability of x less than b minus probability of x less than equal to a, and this is exactly the distribution function. Okay. Right? So first of all, we have that. Okay. Second, x less than b is equal to x less than or equal to a, disjoint union a less than x less than b here. Okay. So this time we use this disjoint union, and again by countable activity, plus probability that. Okay. So this implies that this event has probability which is equal to probability that x less than b minus probability that x less than or equal to a. But by proposition 4.10.6, this is the left limit of the CDF function at x equal to b minus f of a. Okay, so you can see that. Well, so this is from proposition 4.10.8-6, the sixth property here we used here. Oh, no, it's not here. Sorry. Okay. So we apply actually 5 and 6. Okay. This is 5 and this is 6. Okay. And here this we apply proposition 4.10.8 dash the fifth property. Okay. And here both of them by countable activity or just by finite additivity. That's fine. By the finite additivity of P. Right? So that's the sixth. And the third and fourth property, we use the similar argument. Okay. So is equal to x less than a, disjoint union here. Okay. Right, and so again equal to right. So this is implies that probability of A less than or equal to x less than b is equal to probability of x less than b minus probability of x less than a. Okay, so that is the left limit at b minus the CDF of the left limit of the CDF function at a. Okay, so that is the third. And the fourth one, you know that? Okay, this is the disjoint union we have. Okay, so again by finite additivity, Okay, so this is the value of CDF at x equal to b minus the right limit of the CDF function at x equal to a. And the fifth one, okay, we know this is x equal to a is equal to okay, so probability of x equal to a is equal to probability of by 4. Okay, so by 4 we have. Okay. Any questions? Okay, now, since the CDF f of x of a random variable x is an increasing function, okay, now the Riemann still is integral okay, of a constant function f of x equal to 1 with respect to f of x over the interval AB. Right. So f of x becomes to be the integrator. So this is the integrator. And this is the integrand. Okay. The usual Riemann integral is that the integrator is equal to x, the linear function. Okay, so when f of x is capital X, then we know that if f of x equal to x, which is the linear function, then it's also increasing function. So any increasing function can be integrator. Okay. Right, and so the Riemann-Stieltjes integral is an extension of the Riemann integral. Okay. So also we can define the Riemann-Stieltjes integral by Riemann-Stieltjes sum, just like the Riemann sum. Okay. So I will give you a short lecture notes hangout for you to read. Okay. So I will start it from the Riemann-Stieltjes sum. Just like the Riemann sum, all right, when you study calculus 1, okay, and then develop the concept of Riemann-Stieltjes integrals. Okay, so here, so the integrand is 1 here, all right, and the integration interval is this finite cross interval from A to B. Then this integral. So the Riemann-Stieltjes integral x here is f b minus f a. Okay. Okay, so just the endpoint value of the integrator, right? So this is the upper limit, this is the lower limit in the integration. All right? Okay, and so this one is for any AB in between minus infinity and plus infinity here. Right. So you can think about that. If we have dx, remember if the integrator is x, then we know that this is b minus a. Okay? So, so the integrator let me see when the integrator x, say g of x equal to x, which is increasing so we have AB is here. And we know this is GB minus GA. So this is B minus A. Okay. So when you study the lecture notes I will give to you, then you will see that this Riemann-Stieltjes integral is actually this difference. But why is this difference? The difference here is the probability that the random variable has value in this open half-closed interval. Okay. So from proposition 5.1 point B dash 1, we have this Riemann-Stieltjes integral is equal to probability of A less than x less than equal to b, so it's the probability that x in AB. Okay, so for convenience, okay, we define that the Riemann-Stieltjes integral over this half-open, half-closed interval we define to be AB df of x. Okay. So this is the usual notation of Riemann-Stieltjes integrals. Okay. But because of these properties, so we regard that this is over this half-open, half-closed interval. Okay, so it's by definition. And then we have that df(x) is equal to probability that x is in AB. Okay. So this probability, okay, this is the probability of an event of interest described by a random variable, right? This is a very common way we describe an event. And this is indeed is this Riemann-Stieltjes integral. Okay. Specifically over this half-open, half-closed interval. Okay. Now, the power of this notation can be seen here. Since so when we look at this term, when we look at if we have A, B closed interval, then the closed interval actually can be obtained in the way. So this is A minus epsilon up to B. Okay. And we see that the half open, half closed interval were going down. Right? So it's going down as epsilon going down to 0. We usually use epsilon as a small positive number, right? In the epsilon data description. So if epsilon is big, then A minus epsilon would be more to the left-hand side, right? And if epsilon goes to 0, then A minus epsilon will tend to A, right? So the half-open, half-closed interval will going down, become smaller and smaller. So this is the decreasing sequence, okay, of intervals. All right, and so that it will, the limit will be, we will describe that. A minus epsilon, B plus epsilon go down to 0. Okay. All right, so this half-open, half-closed interval will going down. It becomes smaller and smaller, and then the limit it's their intersections. And what is this intersection? What is this intersection? As epsilon goes to 0, this is exactly the closed interval. Okay, any questions about this identity? Okay, so you take the intersections of all A minus epsilon to B. So this is half open, half closed. But when you take the intersection, it comes to a closed interval. Okay, you can look at the figures here. Okay. So this is going to there, to there. All right, so now we see that, so that A minus epsilon B go down to the intersection. And we know that this intersection okay. Now we compute. Okay, so if we take the epsilon go down to 0, and because that this half open, half closed interval becomes to be AB. Okay. Okay. So that this Riemann-Stieltjes integral over the coarse interval can be defined to be the limit here. Okay. And so what's this? Okay. And this is the ordinary notation of the Riemann-Stieltjes integral, and this is the limit. Okay. So that this is f of b minus the limit. Epsilon goes to 0. Okay. So that the point where a minus epsilon will approach to a from the left-hand side. Okay. So this is f of b minus f of a minus. But f of b minus f of a minus, what is that? Which is the probability. So this is the probability of x in AB. Okay? Yes? Second, okay. Oh, yes, thank you. Thank you. Good. All right, so similar argument give us the following proposition. C. So let f of x be the CDF of a random variable x, and I an interval in R. Then the probability of x in I is actually equal to the Riemann-Stieltjes integral with respect to of 1 with respect to the CDF over the interval I. So the notation is here. Okay. All right, so this is the way we express probability of event of interest described by a random variable x. Okay, so this is the original event of interest we are in. Okay, okay, and such a probability actually can be expressed by this notation. Okay, and it is a little bit different from the conventional Riemann-Stieltjes integrals. Okay. Okay. And because conventional Riemann-Stieltjes integrals has this notation here, not A to B there, but indeed. When f is the CDF of random variables, this Riemann-Stieltjes integral is actually equal to the difference. This is well known. But from our proposition here, we know that this is actually the probability of this half open, half closed interval. Okay, that. Okay, and so a good notation for us is here. Okay.
So,
Yes.
given a CDF function,
Yes.
if we have to calculate a PMF function, which was in the quiz yesterday, is this how we calculate it? Because I might have done it wrong in the quiz then.
Well, you know,
How do you
the
calculate a PMF from CDF?
okay, we know from I have erased it, right? Okay. From the CDF, for a general random variable, from CDF, we can compute its PMF. But conversely, it is not able to do that. From the PMF, we can't reconstruct CDF.
Oh, agreed. I was just saying that given a CDF,
Mm-hmm.
how do you calculate PMF?
Well, just like this relation. This is the definition of PMF, right? So the fifth point. So this is actually equal to P of X. By definition, because P of X is just the probability that the random variable exactly equal to A. Okay.
So, in yesterday's quiz,
Yeah.
so CDF was given for a given range, and we were asked to calculate a PMF,
Mm-hmm.
but we were not told like for what value we have to calculate the PMF, the X. So how do you?
Well, you have to compute the X for all X in R, because we define PMF for all X in R, right? Just like the CDF. CDF is a function defined on the whole real line, and the PMF is also a function defined on the whole real line. I know textbook or many other textbooks just ask you to compute the PMF at a point which when X is a possible value.
Yes.
Okay? But for my definition, if you see my lecture notes or my lectures, when I define PMF to be this function. So I define so that P is the domain of the PMF is the set of all real numbers. Okay, and also it's real valued. But I have made remarks that the value of PMF is between 0 and 1, of course, right? So this value should be in between 0 and 1. Okay, and I have also this maybe 2 or 3 additional properties about a PMF. Okay. And so proposition, the first proposition 5.1.8 tells us that the PMF has non-zero value only at point of discontinuity of the CDF. Okay. Yes, please.
The random variable x is a function from simple phase to sigma algebra, or it is just?
It's just, you mean the random variable?
Yeah.
It's just a function from the sample space
To
to the set of real numbers.
Oh, so why? So is having x is belong to an interval?
Oh, yeah, it's just a notation. This is actually this notation means this one. So this event is the same as this event.
Also, it doesn't mean the random.
No. It's just because this notation, okay, is, from my point of view, is not a good one. But it has been used for more than 100 years. Since 19th century, mathematicians describe events about a random value in this way. It's very common in the textbook of probability theory and also in many other disciplines. Statistics, economics, engineering, and mathematics. It has been used more than 100 years. Okay? But the reality is that, what is that? This is actually, so that's why I always repeat the same thing here. Right here or right this way, right? This is the more standard way. Okay? And this is the so-called conventional way. People use that for more than 100 years. I can't change the culture. Because this is the culture in mathematical society. All right? I can't change it. Okay? I'm too old. If I am 20s and I develop a very big theory and become the number one or the top mathematician in the world, then I say I call for a conference and we agree discard this kind of notation. And all the community agree that, then we never mention that ever. Because this is not a good practice. But it has been used very long time. Okay. So you will see every time I always repeat it to do the same thing here, right? Right this way, right this way. Why? Why? This is an intention to do that. To remind you that this notation is actually this meaning. Okay. The value, so the function, just like a function. So we say, and in more rigorous textbook, they described it. Actually, they describe this way. They describe this way. Always put, this is a function of the outcome. Or you can think about this is the, and if you do that, then it's sensible, right? Because this is the value, right? A real number is in this interval. So the meaning of that is actually the meaning for that. Okay. So any rigorous probability theory text will write in this way: x of omega is in this interval, and this says that x of omega is in between. That is greater than a but less than b. Okay. This way. So this always reminds you that a random variable is a function on the sample space. A real value, and usually it's real valued. Of course, you can consider any valued random variable. Categorical value. So, for example, the value can be the colors. Maybe 3 colors: red, blue, and green. Okay, the standard 3-color system. So you have a color value, the random variable. Categorical random value is very typical, especially in machine learning societies. Okay, because you want to classify an item to be one of the classes. Okay. And so that's so maybe every time if when you look at an x, you just put x of omega, then that would make good sense for you. Okay. Other questions? Okay, so from the CDF, we can compute the PMF. Conversely, given PMF, we cannot recover CDF, except the random variable is discrete. Why? For discrete random variable, the CDF is stepwise, right? It's not like this one. This CDF is not a CDF of a discrete random variable because it's not stabilized. Okay, but the PMF at these values were all equal to 0. Okay, because the probability that a random variable has exact value equal to A is 0 in this here, because there is no jump. There is no jump. Okay. Okay. So for random variable has CDF like this, we usually do not talk about the PMF because PMF has much less information than the CDF. But if we talk about discrete random variables, then talking about the CDF is the same as talking about the PMF. Okay, so they contain the same information. So that's why PMF is very important for discrete random variables, but not for general random variables. Okay. Other questions? Okay, so before we take a short break, okay, so I will make a remark. Proposition 5.1.c, so this proposition can be extended to any Borel set E in R, i.e. the probability that the random variable has value in the Borel set B is equal to the Riemann-Stieltjes integral of 1 with respect to the CDF over the Borel set. Okay. Okay. And in our later discussions, okay, when we treat probability or expectation, a lot of things with Riemann-Stieltjes integrals, then we will use notation like this one. Okay, so we will give you the range of the x, okay, over this range that the Riemann-Stieltjes integral is evaluated. Okay, and that they are different, as we can see that. So we know that. Maybe different values. Okay? But for the conventional Riemann-Stieltjes integral, right? here. You see that? A to B. It's very hard for us. What is A to B? Means this one or this or that or there. There are four kinds of different things, right? Okay, and we know that this is just equal to. Okay. So this conventional Riemann-Stieltjes integral is equal to one of them, which is specifically by our convention. And this convention is hinted from this proposition. Okay? Yes? Okay. Hmm? No, different.
It's on 1 point. Does it matter?
Because that, no, it's not on 1 point. It's when A and B are different. So this is the half open, half closed interval. Okay. Right. Because I here, right? Even this four interval has the same endpoints, but they are different. Okay, and because they are different, so that they may have different probabilities. Okay, from this identity there. Okay. So that's why we have to write the Riemann-Stieltjes integrals in this way. This is a modern way, and this is the so-called Lebesgue integral. But I don't want to get into that far way here. Just define what we need here. Okay. Other questions? So in particular, maybe I use here. It's a point, right? So this interval consists of 1 point. And this is what? This is actually. So if the CDF has a jump at A, then this integral is just the jump size, and which is positive. So it's possible for a Riemann-Stieltjes integral over a point, you give you a positive value. Okay? Give a positive value there. So you can think about this proposition 5.1.6 is actually follow from proposition 5.1.b from this information. Okay, and then we create the notation of the Riemann-Stieltjes integral here. Any questions or any points that you feel uncomfortable with that and need more explanation? Yes, please.
Is the mean
in the real line? Well, yes, because the CDF is defined on the real line, so that yes, we usually consider the integration over. This is more general over the Borel set. Okay, because in here the Borel set is a subset of the real line. Yeah, so in this case, but later on, if we consider of random vectors, which means that we consider random variable together, then we must define so-called joint cumulative distribution function, a joint distribution among two or more random variables. And in that time the Riemann-Stieltjes integrals were over not just an interval, will be a Borel set in n-dimensional space. If we consider two random variables, we will consider Borel set in the Euclidean plane. Yeah. Yeah. So at that time, we will give generalization of this notation. Okay. Okay. Just like I think in calculus 1, you study functions of one variable, right? And in calculus 2, you study functions of several variables. Yes. That's why the prerequisite of this course asks you to take calculus 1 and 2, right? So I think, okay, in chapter 6, we will consider more than two random variables, more than one, I'm sorry, two and more random variables together. And we will consider joint distribution there. And so the computation becomes more complicated, a little bit complicated, okay, because we will use one variable calculus to several variable calculus there. Other questions? Okay. Good. Okay. Well, I think we take a 5 minutes break. Okay. All right. Now, we will give a definition of continuous random variable. So a random variable x is called continuous if the probability that x equal to a, so this is the PMF of a, is 0 for all a in R. Or equivalently, if the CDF f of x is continuous, since f a minus is equal to f of a is equal to f of a plus for all a in R. Okay. So a random variable is called continuous if its CDF is a continuous function. And equivalently, it says that the PMF is the zero function, all zero function. Okay. So PMF. Now, I will give a much more stronger condition than continuity. A random variable x is called absolutely continuous if there is a non-negative and integrable function f on R. Okay, so this function is defined on the whole real line. Okay, and it's non-negative, always non-negative, and integrable, such that for any interval I of the real line, the probability that x in I is equal to this Riemann integral. So this Riemann integral actually is a spatial Riemann residual integral with the integrator, which is just the linear function x. Okay, so the integrator is x. So linear function is increasing function. Okay. And then note that okay, it's equal to the conventional Riemann integral with the lower limit a, upper limit b. This is conventional notation. Okay. No matter the I is AB, open set, B, or AB. This is because the integrator x is a continuous increasing function there. So it was specifically a point is 0, okay? So it's very special because the integrator is the linear function x self. Okay? Okay, but we like to express that in this way, okay? Because we want to use the same notation here, okay? And regard Riemann integral as the Riemann residual integral, okay? There, and with different integrator here. Okay? So this is a linear function as integrator. Okay, so okay, so to check that a random variable is absolutely continuous, you have to find such a function f, okay, non-negative, integrable, and you have to check that for any interval I, this probability can be evaluated by this Riemann residual integral. Yeah. And there are some points to make. So we mark here. The first one, because that the total event has probability 1, and we know that the total event is equal to event that the random variable has value in between negative infinity to positive infinity, right? So it's because it's a real value function. Okay, so this is equal to the event, and so that okay, it's here. Okay, and so the conventional evaluation. So a necessary condition is here that if we integrate this f of x function from minus infinity to infinity, then this integral is equal to 1. This is necessary condition. So if you pick up a function f of x and you find that this integral is not equal to 1, then it's not a 1 for this. Okay. So this is the condition. Second, the function f is called a probability density function called PDF of x okay. So you may think about that probability like a mass, right? Now, and the mass is just integrate the mass probability function just like in physics, right? Over the same range. Okay. So this is called probability density function. Okay. The third one, of course, that okay, because we have this, so this implies that x is a continuous random variable. Okay. So if x is absolutely continuous, okay, so if it is absolutely continuous, then x is a continuous random variable. So absolute continuity is stronger than continuity. Okay, it's stronger. Okay. It is sufficient to check that the distribution function, okay, right? So it's sufficient to check whether the distribution function can be obtained by this indefinite interval. Okay, so this is the indefinite interval here. The reason why this is sufficient, because by definition we have to check here. Okay, we have to check that when you have for every interval I, you have this. Okay, but why this is enough? Okay, so this the reason is that from proposition, again from proposition 5.1 to 1b, we know that probability that x is the random variable has value in this half open half closed interval x f b minus f a. Okay, and so this is actually minus okay. And from our usual Riemann integral, the problem Riemann integral, this is actually here, and this is actually equal to, so to give us this one. Oh. Okay. All right. Here. And also, for example, this is FB minus FA minus here. All right, and so this is the same. Okay. And again, okay. If you are if I will write that way, it's more instructive. We will say here. So this is okay in here. Okay, maybe I use my original argument, which is more elementary, because that is use property of integral. And okay, minus all right. So this is a minus, but we know that the a minus is equal to a because we are evaluating the Riemann integral, so that at one point the integration, the Riemann integral always is 0. Okay, so we can replace the a minus to a. Okay, and again, so this is equal to ab. Okay. Right, and so similar argument give us v of x in interval equal to dx. Okay, for any interval I in R. So to check if we can find a PDF for a random variable, okay, then you check that the function f of x is non-negative integrable, and this indefinite integral is equal to the CDF of the function of the random variable. Okay. Next, I would like to make a point about PDF. So if x is an absolutely continuous, later on we will say AC, okay? random variable with a PDF of x. Then, so if x is absolutely continuous with a PDF, then x has infinitely many PDFs. So for an absolutely continuous random variable, it has infinitely many PDFs. Okay, so then you have even many possible choices for a PDF. And usually we select one, which is very nice. For example, it's continuous, right? Almost all. And if it's not possible to select a continuous PDF, then you will select a PDF which is discontinuous. It's less points of discontinuity. Okay, so you try your best to find one which is good for you. Okay, because there are infinitely many possible choices. Why? Right. So to see this, we let. So suppose we have one, right? P of f of x. Then we construct GAX. We define function. So GAX is equal to f of x if x is not equal to a, and if it's x plus 1 if x equal to a. So f of x and GAX. So suppose that. So this is this is a PDF here, and we construct another function. Okay, so suppose we pick up an a here. We add 1. All right, so that g of x would be the same, except at x equal to a. So this is g at a. So these two functions are different. Okay, they are different at one point here. Okay. But for each a and r. All right. So then we have. So when we evaluate. Right, so we know that we have GAX non-negative and integrable, and we have that this is equal to for any interval I in R. So that's GA of x is a PDF of x for any A in R. Okay, so we can find infinitely many other PDFs there. Okay. Any questions? Yes? You mean the PMF? Yes. For continuous random variable, the PMF function, this probability max function, is identically to 0 function. It's identical to 0 function. Yeah. Because by definition, that because if we call a random variable to be continuous, if this probability is 0, okay, and this probability by our definition is just the PMF function at A here. So this is 0 for all A. This is just by definition. And this is equivalent to say that the CDF function is continuous. Any questions? Okay, so I have to emphasize that every time when we find a PDF for an absolute continuous random variables, we usually find one which has a good property. Yeah. You try your best to do that. Yeah. Right. Okay, so we will have midterm exam number 1 the coming Thursday. So good luck for you. And the exam will begin at 12:40. So please come here earlier. And by the way, the solution of a few quizzes will be given before next morning. Okay, so I'll ask you to, I think the TA will ask you to come to lab 608 in the EE6 building to pick up solutions. Okay, all right.